You know, Alex, I spent 3 days last week printing this ornate Art Deco jewelry box. Woke up at 2 o'clock a.m. like a kid on Christmas just to check the build plate. It looked perfect. Then I tried to quickly snap off the supports with a pair of needle nose pliers and ended up taking a chunk of the actual lid right out with it. It looked like a beaver had been snacking on my geometry.
The classic just one more tug tragedy. I've seen that look on your face before. It's the face of a man who just realized he has to start a 40-hour print over because he was impatient for 30 seconds.
It's the heartbreak of the maker world, truly. We talk so much about the machines, the SLA resins, the FDM filaments, the SLS lasers, but the real soul of the craft happens after the machine says it's finished. If the printer is the oven, post-processing is the frosting, the plating, and the seasoning. You can bake a cake, but if you serve it in a crumpled tin with half the crust stuck to the bottom, nobody cares how good the flour was.
So today we're talking about how not to be a beaver. We're diving into post-processing because let's be honest, fresh off the plate, most 3D prints they look like 3D prints. They've got those telltale ridges, the support scars, the I was made by a robot vibe. How do we get them to look like they belong in a high-end gallery or a professional engine bay?
It's a three-headed dragon, really. You've got subtractive methods where you're taking stuff away, additive where you're building it up, and then the weird sciencey stuff where you're actually changing the molecular ego of the material.
Let's start with the basics. You mentioned the beaver incident. Support removal is the first hurdle. If you're using something like a Formlabs SLA printer, you've got these tiny touch points, but they still leave a mark. Is there a way to do it that doesn't involve prayer and a pair of pliers?
Soluble supports. That's the dream, Alex. If you got a dual extrusion setup, you can print your supports in a material that just vanishes in water or a specific chemical bath. It's like magic. You drop a complex, spindly mess into a tank, walk away, and come back to a pristine part. But for most of us, it's mechanical. The trick isn't pulling, it's snipping. Use flush cutters, leave a tiny bit of the stub, and then tackle it with the abrasives. If you try to break the bond at the surface, the material will almost always take a piece of the mothership with it.
Okay, so we've got the supports off. Now the part feels like a vinyl record, lots of grooves. You mentioned subtractive methods. I assume that's where the elbow grease comes in?
Sanding is the oldest craft in the book, and it's still the king. But people go at it all wrong. They grab a piece of 80 grit and start rubbing like they're trying to start a fire. With plastics, especially FDM prints, you generate heat. If you get that plastic too warm, it softens, it smears, and suddenly you're not sanding, you're just moving warm goo around.
So what, wet sanding?
Exactly. A little water, a little patience. Start coarse to kill the layer lines, but you've got to move through the grits like you're climbing a ladder. If you skip from 120 to 400, you're just polishing the scratches you made earlier. You want to see that surface turn into a uniform mat before you even think about moving up. By the time you hit 2000 grit and some polishing compound, that plastic should look like glass.
That's great for aesthetics. But what about the engineers listening? I was reading some of the research from the ACM papers you sent over, and they were talking about how professionals don't just care about how it looks, but how it fits.
That's where subtractive goes high tech. If I'm making a housing for a bearing, the 3D printer is rarely accurate enough to hit a thousandth of an inch tolerance straight off the hop. Professionals will actually overprint a part, make it a hair too thick, and then put it on a traditional CNC mill or a lathe. We're combining the 21st century with the 20th. You use the printer to get the complex shape, and you use the mill to get the precision. It's a beautiful marriage.
It's like you're giving the robot a haircut.
A very, very precise haircut.
Let's flip the script. Additive post-processing. You're putting stuff on the print. Why would I do that instead of just printing it right the first time?
Because sometimes the printer can't give the material the properties it needs. Think about resin infiltration. If you're printing with something like an SLS powder bed like the Fuse systems, the parts are incredibly strong, but they can be slightly porous. You can dip them or vacuum infuse them with resins that soak into the microscopic voids. It's like giving the part a skeleton of steel. It makes it airtight, watertight, and significantly tougher.
I've seen people talking about electroplating too. That seems like the ultimate cheating for makers. How does that work?
It's not cheating, it's alchemy. You take a plastic print, coat it in a conductive paint, usually something silver or copper-based, and then you dunk it in a tank with an anode and a power supply. You're literally growing a skin of real metal over the plastic. You get the lightweight, complex geometry of 3D printing, but the surface hardness, conductivity, and let's be honest, the shiny wow factor of chrome or nickel.
That's a long way from the beaver bitten jewelry box lid.
A very long way. But even simple painting is additive. A good high build primer is a miracle in a can. It fills those microscopic layer valleys so you don't have to sand until your fingers bleed.
We've covered taking away and adding to. Now, what about this property changing category? This sounds like the stuff they don't tell you in the hobbyist forums.
This is where we get into the secret sauce. Take annealing, for example. If you print in something like PLA or certain high temp filaments, the molecules are all stressed out from being shoved through a tiny nozzle and cooled rapidly. They're like people in a crowded elevator. Annealing is putting that part in a controlled oven at a specific temperature. It lets those molecules relax and reorganize.
So you're giving your 3D print a spa day?
A very hot, very precise spa day, it can make the part significantly more heat resistant and stronger. But, and this is a big but, the part will usually shrink or warp slightly. You have to account for that in your design. It's a dance. You're trading a bit of dimensional stability for a lot of mechanical integrity.
And what about chemical vapor smoothing? I've seen those videos where a rough, matte print suddenly turns into a shiny lollipop in seconds.
It's mesmerizing, isn't it? You're using a solvent like acetone for ABS or specialized fluids for other materials to slightly melt the outermost layer of the print. The surface tension of the liquid plastic pulls itself flat, erasing all the layer lines. It's fast, and it treats the inside of internal channels you could never reach with sandpaper. But you have to be careful. You're essentially melting your work. Too long in the vapor, and your sharp edges turn into marshmallows.
We've talked a lot about the how, but the research paper you found, the one about how professionals use these digital workflows, pointed out something interesting. It's not just about the tools, it's about the machine control as a design space.
That really struck a chord with me. We often treat the printer like a black box. You put a file in, you get a part out. But the pros, the people making low-volume commercial products, they're tweaking the G-code, they're changing how the machine moves to create specific textures or strengths. They're treating the tool itself like a brush.
It's that realization that the software and the hardware aren't just one-way streets. The material constraints aren't just obstacles, they're actually dimensions of the design. If you know you're going to tumble apart in an abrasive media for 24 hours, you design the edges to be a bit sharper because you know they're going to get rounded off.
Exactly. You're designing for the process, not just the shape. It reminds me of when I first started blacksmithing. You don't just hit the iron. You have to know how the iron wants to move when it's at a cherry red heat. 3D printing is no different. You're just working with a much smaller, much hotter fire.
So, for the person sitting in their garage right now looking at a print that just finished, what's the one takeaway? What's the first thing they should do to step up their game?
Put the pliers down, just for a second. Look at the part and ask yourself, what is this part's job? If it needs to be pretty, grab the wet sandpaper. If it needs to be strong, look into annealing or resin infiltration. But most importantly, don't treat the post-processing as a chore you have to get through. Treat it as the final stage of the craft. That's where you take the robot out of the object and put the maker into it.
Spoken like a man who has finally finished his jewelry box.
Oh, I finished it. It's currently holding my collection of mismatched screws I'm too stubborn to throw away. It looks like $1 million, even if the contents are worth about 3 cents.
And that's the Tiger Den way. Professional results for 3-cent problems.
You're not wrong. Next time, I think we should talk about 3D scanning. Because why design something from scratch when you can just steal the soul of an existing object, right?
Stealing the soul. We really need to work on your terminology, Tiger.
Stay dusty, everyone.